Welcome back, everybody. This is our video solution to problem 4 from Quiz 3, Fall 2023, Math 307, Linear Algebra at Cal State Fullerton. In this problem, we're given a whole bunch of functions, and we want to determine whether or not they're linear maps. Now, the problem says we don't have to explain our work, but in this video, we're going to do that. All right, so let's give it a go. In part A, we're given a function from R3 to R, defined by taking an element of R3, so x, y, z, multiplying the components together, and then tripling the answer. Now, in class we talked about how if you want to detect whether or not something is a linear map, and it's given in this sort of form, right, where you have a map from Rm to Rn, you want to look for linear combinations of the inputs. So things like 2x plus 3z, right? That would be a linear combination of the inputs. When you have those as the output of the function, you should expect that you're getting a linear map. But if you're using other operations, like multiplying things together, you shouldn't expect to get a linear map. And sure enough here, we could test, right? We know for a linear map, if you have t of u plus v, this should be tu plus tv. This is the additivity condition for being a linear map. Well, what if we try that here with, say, t111? And then I'm going to add to it t111. Now, the way I apply t is I multiply the numbers and then multiply by 3. So this would just be 3 plus 3, which is 6. But if I add 111 and 111 together, I'll get 222. And if I apply t to that, I'm going to get 2 by 2 by 2, which is 8, by 3 is 24. Those are not the same thing. So I can't just break up t of 222 is t of 111 plus t of 111. So t here is not linear. All right, let's try B. I'm given a vector space V of infinitely differentiable functions from R to R. All right, so that means I can take as many derivatives as I like, and I always get back a differentiable function. All right, and then what is this t? That is going to be the derivative map. Right? So I start with a differentiable function, right? It's infinitely differentiable. I take the derivative. It still has to be infinitely differentiable. Is this a linear map? Well, the answer here is going to be yes, because we all took Calc 1 and we know that the derivative is additive and homogeneous. So if I have f and g in V, and I apply t to the sum, then this is going to be the derivative of the sum. But the derivative of a sum is the sum of the derivatives. So this will be f prime plus g prime. But f prime is tf, and g prime is tg. Hey, there's our additivity condition. All right, but of course, there's another part of being a linear map, right? You need this homogeneity. So if I took t of cu, this should be the same thing as c times tu, right? I can pull scalars out. So what if I had some scalar, and I applied t to c times f? Then this would be cf prime. I take the derivative of cf. But again, we know when you take the derivative, you can pull constants out. So this is equal to c times f prime, which is c times tf. And so in this case, yes, t is linear. All right, part C. We have a function t from the reals to the reals, and all it does is take the input and add 4 to it. Now that looks pretty linear, right? If you were in high school algebra and they said, is this a linear function? Of course it's a linear function, right? It's a line. But you remember we had this really nice property of linear maps, which is when you apply a linear map to the 0 vector, you have to get out 0. Well, what happens here? If I apply t to 0, I get 0 plus 4, which is 4. Which is not 0. And so that tells you that t is not linear. All right, let's go on to D. D, we have a vector space of continuous functions, we'll call it x, from the interval ab to the real numbers, where here a is less than b. So you don't get some weird thing like, the closed interval from 5 to -2. Okay, and now we're going to define a map from this space of continuous functions to the reals. And the way we're going to do it is by, you give it a continuous function, and you just integrate it from a to b. Now, that this actually makes sense at all relies on you knowing that you can actually integrate a continuous function. Okay, but again, this is something that you learned in your calculus course. Not only that, but, well, is t going to be linear? Well, let's check. What if I did t of f plus g? This would be the integral from a to b of f plus g dx. And this is a rule we all learned in our calculus course, that the integral of a sum is the sum of the integrals. So I get the integral of f from a to b plus the integral of g from a to b. But this is precisely tf plus tg. Okay, but we also know if I take t of cf, this will be the integral from a to b of cf, and we know we can pull constants out of integrals. So this is c times the integral from a to b, f dx, but this is again c tf. So there we go, t is linear. All right, the final one, we have a map from C3 to C3. And what it's going to do is take a triple of complex numbers. It's going to multiply the first one by 5. Then it'll multiply the first one by 2i and add it to the third one multiplied by 3. Then it will negate the second one and add it to 6 times the third one. Now you notice in this case, all we're doing is either, well, in this case, just taking 5 times something, right? It's a nice scalar multiple. Here we're doing a scalar multiple times u and a scalar multiple times v and then adding those together. Here we're taking a scalar multiple of v and we're taking a scalar multiple of w and then we're adding them together. All we're using are addition and scalar multiplication. And when you do that, you're going to get a linear map. So in this case, t is linear. Now we could go through, right, and test these. So I'll do one of them, show you what it's going to look like, and I'll let you do the other. So let's assume that we have t of, let's see, u v w, and then how about we'll add to that t of, I don't know, how about x, y, z. So this would be 5u, comma, 2iu plus 3w, comma, negative v plus 6w, right? That's just coming from the definition, plus, then I'll have 5x, comma, 2i times x, plus 3 times z, comma, negative y plus 6z. Okay, I can put these together, and I'm going to get 5u plus 5x, but man, let me just factor the 5 out, right? I'll get 5u plus x. Then I'll have negative 2iu plus 3w, 2i x plus 3z. When I add those together, I'll again factor out the 2i. So I'll get 2i times u plus x plus, okay, now I have 3w and 3z, so let's factor out the 3. I'll get w plus z. Then when I put these together, I have negative v and negative y. Well, that's just negative v plus y. And then I have 6w and 6z. I'll factor out the 6 to get w plus z. But now this is exactly what I would get if I took t and I applied it to u plus x, comma, v plus y, comma, w plus z. Okay, and I'll take a second to make sure like that worked out. Let's see, if I did t applied to this, I would have to take 5 times the first component. So 5 times u plus x. Hey, that's what I got up here. Then I would have to take 2i times the first component. Okay, oh, look, 2i times u plus x. And 3 times the last component. Hey, 3 times w plus z. And then finally, I'd take the negation of the second component, so negative v plus y, and 6 times the last component, so 6 times w plus z. Hey, we did it. All right, so I'll let you check that homogeneity works, but it's going to work pretty much in the same way. All right, so that's the end of our video solutions to Quiz 3. We'll see everybody next time.